those devices, and here we have a simple comparison of those emerging devices with mainstream technologies in terms of those metrics like cell area, multi-bit voltage, read time, retention, endurance, energy, and so on. So if you compare that, okay, in terms of F square, so those emerging memories typically depends, okay, depending on the layout, can be tens of F square or can be as small as 4F square. So this kind of number you see is somewhere, let's say, below SRAM, right? And comparable maybe to NOR flash, but definitely it's not NAND flash, because these days, NAND flash will have 3D, and the equivalent size for each bit is so small. And then, as I said, like phase change memory ARM can do multi-bit, 2-bit, or even 3-bit possible. STT-MRAM is just 1 bit. And the voltage, for example, here STT-RAM can operate like below 1 volt, and the ARM phase change may be probably less than 3 volts. So this is better than flash. And but this ARM phase change is still higher than the DRAM or SRAM, like around 1 volt. And the read time, those typically can be read like 10 nanoseconds or below. So this is much faster than the flash, comparable with DRAM, but of course slower than SRAM. And the retention, those are non-volatile memory, so retention should be good, similar as flash. And the endurance, okay, STT-MRAM is supposed to have good endurance, like 10 to the power 15. But in reality, okay, from the Intel's recent result, it's only like 10 to the power 6 or 10 to the power 7 from the real chip. But fundamentally, this one should be good, okay. And phase change memory and ARM has some physical mechanisms to degrade the on-off ratio over cycles. So typically they are like 10 to the power 6 or maybe 10 to the power 9. Some papers reporting like 10 to the power 12. So those are some data from the literature. But from the, let's say, the real chip or product point of view, like ARM phase change, for example, ARM maybe a few thousand cycles, phase change maybe 10 to the power 6. So like 3dx point, I don't know the exact number, but I don't expect that to be more than 10 to the power 6.
For phase change, how did you say you implement multiple states? Is it like the percentage of
yeah, exactly. So we will discuss that in more details, but exactly as the volume of the amorphous state. So if you look at those metrics here, and you can conclude something from here. For example, if you look at the STT-MRAM and SRAM, so you will see that STT-MRAM is much smaller in the cell area, at least a few times smaller, and the voltage is compatible, like less than 1 volt, and the time is a few nanoseconds, not as fast as SRAM, 1 nanosecond, but you can do like 5 nanoseconds, it's okay. And the endurance is supposed to be good, but there are some practical engineering issues to limit the endurance. We'll talk about that later maybe. And then the STT-MRAM may be a good replacement for the SRAM, probably for the last level cache, L3 or L4 cache, where the speed is not like 1 nanosecond. So then the STT-MRAM, if you can do that, then you can make the L3 or L4 cache even larger, because STT-MRAM is smaller in cell size. And one more advantage is that this is non-volatile memory. So you can power off the cache if you don't use it, right? So SRAM, always leak. So this is possibly another advantage. So this is a potential application, okay?
So until today, there's still nothing that can beat the endurance that DRAM paths and still maintain speed.
Yeah, so if you want to have this is what we discussed. I think at the end of the DRAM lecture, I said there's no emerging technology that can replace DRAM at this moment. Yeah. And SRAM, maybe the L3 or L4 cache, maybe, but for L1 and L2, there's no competitors there.
If we can have a non-volatile memory and have other similar performance as SRAM, what will be the tangible changes for the real application?
Oh, you can do this so-called dynamic power gating, right? So you can turn off your power supply very frequently, right, without losing your data. Like your app, you are running some programs, and if you switch to another app, you can do this so-called context switch, and you can save the data there without losing the data, and basically you can save a lot of power if you can do that.
How like a few orders of power, or just?
I don't have a number here, but I think there are papers doing that kind of research to estimate the benefits. Yeah. So, but right now the problem is it's not as fast as SRAM, so you cannot replace all the SRAM. And phase change and RRAM is cannot replace either DRAM or NAND flash, so they can only be regarded as somewhere between DRAM and the flash. Okay, if you look at the specs here. So that's why we have this kind of a new hierarchy. If we want to position those emerging technology into this hierarchy. So as I said, STT-MRAM may be the last level cache replacement if the endurance can be further improved. So the challenge for today's endurance degradation is due to the process, fabrication process. It's not due to the fundamental physics there. And the RRAM of exchange, especially 3D version of that, like the 3D exponent, can be this so-called storage class memory between the main memory and the SSD. You can think it's the higher end of SSD. So this is exactly what Intel and Micron is trying to sell.
So no flash there.
This is for standalone memory application. Of course, for all those emerging memories, they have the potential to be compatible with logic. If you can further scale down the programming voltage for RRAM phase change, they can replace the eFlash for the embedded memory beyond 28.
I think Intel just announced an embedded memory with RRAM.
Yeah, Intel has 2 papers in this year's ISCC. They have embedded RRAM and embedded MRAM process at their 22 nanometer FFL platform. Yeah. So this is the landscape for the emerging memories. And let's quickly go through this. I think we have shown this at the very beginning of the semester. So this is a trend for the trade-off between the speed and the capacity or density or cost. So then the 3D NAND is moving in this direction, and 3D DRAM is moving in this direction. Of course, you have known that 3D NAND and 3D DRAM are different. One is monolithic 3D, the other one, this one is TSV-based 3D stacking, so they are different. We have talked about that. And the storage class memory, so somewhere in between, like the RRAM phase change memory on the 3D exponent is in this space. And in the recent years, so this is a summary I put together a few years back to look at the data from the major conferences like ISCC or the VLSI Symposium on the prototype chip capacity for those emerging memories. Like the phase change memory RRAM can go to like gigabit level, but still NAND flash is already, this is a few years back. At that time it's 128 gigabit. These days it's 1 terabit. So it's very hard to catch that density. Okay. STT-MRAM is for like cache replacement, so the capacity is still like 64 megabit or 128 or 256 megabits. I know every spin is advertising like their 1 gigabit STT MRAM, but still, in general, STT MRAM's capacity is less. So this is the capacity. And then if you look at the performance in terms of the bandwidth, and read bandwidth, so the flash is in this corner. So depending on low flash or NAND flash, you know NAND is slow in the read, but maybe faster in the write because you do the block. So then it's in this corner. And then the emerging memories like ARA, STT-MRAM, they can generally outperform the flash by 10 times in terms of the bandwidth. Okay, so this is a very brief overview of the emerging memories. We're going to have more discussions later into each technology. But in the next, we are going to talk about some generic array architectures that those emerging memories share. So the first one is called OneT1R Array, and it's one transistor, one resistor array. And this is the array organization. So you have one transistor, control one resistor. This resistor can be RRAM, can be STT-MRAM, or can be phase change memory. So in general, those are resistance-based memory. So we use resistor to represent that. Or maybe a better way is to maybe have an arrow here. So you know this is a variable resistor. You can change the resistance. So this, if you look at this array architecture, so do you think this is similar to something? Do you look familiar?
Sure.
Like what?
DRAM.
DRAM, right? So if you replace this resistor with the cap, then it's DRAM. So also this is like no flash. If you get rid of the resistor and then you change this to be floating gate, then it's like no flash. So then the word line controls the gate of the transistor, and then the transistor, let's say source line, and then the other end attached to the resistor, and then you have the bit line. So if you look at the 3D view, it's more like something like this, right? So then that means this resistor actually is integrated here. Okay, so you can do this as the drain contact between the metal wire and the drain of this transistor. So this is lowest level you can put the resistor here. So essentially those resistors are some oxide or chalcogenate material, and you deposit that contact layer with those material. So this is what you can do, but of course in many vendors, I believe including TSMC and Intel, they put those emerging memories to the upper metal layers, like between metal 3, metal 4. So essentially where you put those is the contact layer. So can be this metal 1 contact, or can be the contact between metal 3 and metal 4. So you just need to dig a hole and then connect to the transistor drain underneath if it's on the metal 3 or metal 4.
And why you want to do that? Why you want to do
Because the process compatibility, right? So the you don't want, especially like those phase change material like chalcogenide or STT-MRAM, those magnetic material, not very compatible, friendly to the CMOS front-end process. They are very strange material and maybe contaminate your transistor. So, and also the thermal budget, all those considerations. So you may put those at top. I have seen the RRAM, oxide RRAM material put onto the M1, M1, this contact. So this is because that one is simple. The RRAM is just one oxide. So you can do that. If you look at this kind of cell layout, then typically you can realize like a 12F square if the W over L is 1. Okay. Then if you do a normal isolated transistor kind of layout, you get like 12F squared, like 4F times 3F. Or more aggressively, you can get 6F squared, right? Why is that? If you do something, you can get 6F squared in principle.
Like with the DRAM.
In like DRAM, as I just said, so this is like DRAM. So, but in that case, you have to rotate your transistor with some angle, the channel, right? So you recall the DRAM discussions. So if you do that, then you can get 6F squared. If you really push. But I don't see many companies are doing that, because in this case, your density, you are not competing with DRAM or NAND flash directly, so the density can be relaxed a little bit. So this is OneT1R Array, and this transistor is useful to individually select which resistor to read or write. And then this is a typical write scheme, right? For example, if you write, we have the set and the reset. Basically, set is, let's say, 0 to 1, and the reset is 1 to 0. Because the bipolar nature, when we talk about the RRAM or STM RAM, we need to use bipolar voltage to switch it. So then you may have to do this. So if, for example, if this is a selected cell, then what you want to do is to turn on the WL. So you turn on the WL here, this one. So then this transistor is on. And then if you set, then you apply the set pulse to the bit line. This is bit line. So current will flow this way. This is grounded. The source line is grounded. Okay, the current will flow this way. So you set the device. And if you want to reset, okay, then still you need to turn on the word line here. So the transistor is on. And you need to reverse the voltage polarity. But normally on chip you don't have negative voltage, okay? So, but you can simply just reverse the source line, the bit line, and row. So let's say the reset voltage is coming to the source line. This is source line. So the current will flow this way, and then your bit line is grounded. So you just reverse the source line, bit line's voltage. Then you can have the bidirectional bipolar switching. And then for the read, it's simple. So you just still need to turn on this word line, and then you just attach the bit line to some read voltage or to your sense amp with smaller voltage. So then you can read the state by reading the current or reading the voltage. So this is the OneT1R. And the challenge for the OneT1R scaling is that you need to somehow sometimes size up the W over L of that transistor. If the device write current is large, so your transistor needs to deliver that current to program or write your device. So here I have some summary of the data from the literature for different technology. Like RRAM, very scattered because very different kinds of material used. And STT-MRAM and the phase changing memory. So this is respect to the technology node, the cell size. And here we also draw the line for the current drivability of the transistor at different W over L. This is for logic transistor, I believe. And you can see that this phase changing memory, large current, hundreds of micron, even at this like 50 nanometer load. So that means your transistor needs to be very large to pass that 100 micron, because each transistor, typically, if you are familiar with the circuit design, then one transistor can give you only like 10 micron, or so this, if you need hundreds of microns, then you need to size up the transistor very aggressively. That means your cell area cannot be like 10F squared, 12F squared. So if you look at that, so you may end up with like 30F squared, 50F squared And actually, I look at Intel's design. That you mentioned the R1 design. I calculate that is 80F squared to 100F squared. If you look at the cell size. So that's a challenge. Okay, we have to reduce the programming current for those technology. And for phase change memory is good because it's bad or good. Let's say bad first, because the current is large. But the good news is that the phase change memory current will scale with the dimension of the cell, because depending on how much material you need to heat. So if you scale down, then the current will decrease. So this is for the phase change memory. But for the other R1, there's no correlation between the technology node and the current. In that case, we have to really engineer the material, which is not easy. So this is the challenge in the scaling for OneT1R. And then let's talk about the cross point, this X point, or crossbar array. So this is a crossbar array. So basically you get rid of the transistor in the array. And the cell resistor is in series with some device called selector. Okay, we will talk about in more details what is selector in the next couple of slides. But if you look at the 3D view, so basically you have the word line and bit line perpendicular to each other, and then at each cross point you will have this kind of one selector, one resistor stack, 1S, 1R. Sometimes we call it 1S, 1R. So selector, and then R1 or phase change memory. So STT-MRAM is challenging to be used in the cross-point array because the on-off ratio of the STT-MRAM is really small. And we will see there are some challenges in the readout margin if we consider the so-called sneak path, which will degrade the readout margin. And if you do this, then in principle, of course, you can achieve 4F squared for the each cell, because you know this is one wire is 2F, so you have 2F times 2F for the word line spacing, 2F for the bit line spacing, then that's the bit line pitch, word line pitch, then it's 2F by 2F, 4F squared. So let's look at the write and read operation scheme for the crossbar array. So it's a little bit tricky. You have to play this carefully. Okay. So for example, in this first we have some so-called V/2 write scheme, and this is for bipolar operation. For example, the R1. So let's say this is a selected cell, and then we need to apply, let's say, the red line is VDD, the V write, or V write to the red line, and then we ground the green line. So then this cell is selected because it has this write voltage across this cell. Okay, you are going to write, let's say this, if you think this is set, you are going to set this device. But the problem is for other unselected cells, you have to be careful. Okay. So what you want to do here is to apply V/2, V write over 2 to all the other lines. Those black lines are all V/2. So the reason you want to do this is for the selected cell, they share the same row here. So that means for this unselected cell, you don't want to write. Okay, so you need to prevent the disturb. So you also if you use the flash words, you want to inhibit. So how do you do that? Then you apply V/2 here. So you look at the voltage drop across this cell is V minus V/2. So actually you have V/2 across this cell. So actually you can tell that along the same row, all the cells will have V over 2 across that. And this is half select. And you hope that half of the right voltage will not change the state. Okay. And similarly for the shared column here, this green line, you can check that all the cells will have V over 2 across that. Okay. So this is also half selected. And then for the rest, like those cells here, you can see that both row and column are V over 2. The actual voltage across that is 0, so they don't have the voltage. So this is how you do the set. If you do the reset, you need to change the polarity, and then you just change the red line and the green line. If you still want to reset this cell, then the green, let's say you apply V right to the column and ground this row. And again, for the other unselected row or column, you have V over 2. Then again, you will have this half selected cells along the selected column or selected row. So this is the write operation.